Yeah, thanks a lot for the invitation. I'll apologize in advance. I've had this sort of lingering respiratory thing, so I might have coughing fits throughout, so to entertain you. So please come up as it goes and ask questions. That will kind of improve things for everyone, I think. Okay, so I'm going to be talking about scalable Bayesian inference. So I'll start out with a motivation and background, and then I'm going to have like two subparts. The first part is on big N, or big sample size, and so you can very roughly think about two different types of scalability. The one would be where you have a data set that's really has enormous sample size, but the complexity per subject is not that high, and so you might be trying to do a logistic regression or something like that, and you might have millions of subjects or hundreds of millions of subjects, and you want to do something like logistic regression that's not that complicated. Okay, and so that'll be the kind of first chunk of the talk, and then probably more after the break, I'll focus more on high-dimensional data, which means that you have a lot of dimension per, or complexity per replicate, so per subject if it's a biomedical study. And that could also be a big model. And so if you had like a deep neural network or some non-parametric Bayesian model with many parameters, that would essentially be a kind of big P problem. And so we can roughly think about big N and big P. And big N, I would say, would be an area that's much more well addressed by the existing literature, and big P is more of an emerging area for which there's some methods in particular cases, but not sort of a lack of overarching methods that can deal with broad problems. Okay, so one thing I'd like to do partly in this tutorial is to motivate more of you to work on Bayesian methods, because I think that there's sort of vast open problems and a huge potential for new research that can have a really big impact in broad variety of areas, in industry, science, policy, etc. Okay, and so obviously there's a huge literature already focused on big data, but I'd say most of the focus has obviously been on optimization methods, and so as a result there's potentially, I would say, orders of magnitude more people working on trying to do optimization in really large complicated data contexts than there are people working on Bayesian methods that do appropriate uncertainty quantification. And I think that that's really the core of statistics, and really important in a lot of machine learning applications is we need to think more about uncertainty and doing valid inferences in the presence of uncertainty. And so if we have some algorithm that produces what I'd call a point estimate, it might be a point estimate for a prediction for an input-output relationship. I think that really kind of falls short in a lot of applications, and we can't be just doing that. We need to be actually characterizing uncertainty in our predictions, and importantly, not just in a black box for prediction, but in something that's really interpretable. So that's really key, I think, in science and in other application areas. And so we want to go beyond optimization methods. So again, most of the literature, I would say, on scalability is on rapidly obtaining what I might call a point estimate. It might be a point estimate for parameters or a point estimate for an input-output predictive model, okay? And we'd like to be able to do that even when the sample size N and the overall size of the data is immense. I would also advocate for people working less in a bandwagon-y way, I would say that there's been a huge focus in statistics and machine learning on people working on very similar things, on, for example, linear regression, certain types of imaging problems, etc. But there's actually huge open problems that remain essentially untouched, where we have almost no methods that are reasonable at all for these types of problems. And so many of those problems fall into the sciences, for example. We might want to do something like precision medicine. So we have millions of observations observed on each subject for different biomarkers. They might be genomic, they might be neuroscience biomarkers, and we'd like to use that to predict patient health and to target treatment for different diseases, okay? And we'd like to do something like that, and we have really no idea how to do it currently, okay? So I would again advocate for people working on those types of problems, on different types of problems, try to avoid working on the same problems everyone else is working on. Okay, so my focus is in general on probability models. This is obviously a tutorial on scalable Bayesian inference per se, but I would say it's often useful to take the Bayesian paradigm, which is really nice in terms of using probability to characterize learning from complicated data, and take a little step away sometimes. And so the main thing is that we have a really nice approach for learning from different types of data, and we're characterizing uncertainty in that learning and in our inferences and predictions in a valid way. And that's really useful if we're using a probability model, and Bayesian statistics is one type of formulation of that. Okay, so we'd like to have some sort of general probabilistic inference algorithms from complex data. We'd like to be able to handle arbitrarily complex probability models. And so, often nowadays data are really increasingly complicated, and we need to be able to model the complexity of the data. I've been mentioning this precision medicine application. You could think of data from patients coming into healthcare clinic, and there's a lot of censoring, observations collected over time, selection bias, which is something which is incredibly important to take into account. We can have missing data that's informatively missing. And if we don't characterize this sort of complexity, if we just kind of throw some sort of neural network or some algorithm at it, putting all this data together, not taking into account the selection that occurs of the data that we observe relative to the data in the general population, then we're going to get kind of bogus garbage, basically, out of the results. Okay, so we'd like the algorithms to be scalable to huge data, potentially using many computers. Okay, and accurate uncertainty quantification is a critical issue. I would say that a lot of this scalable Bayes inference, and I'll touch on this, has been focused on algorithms such as variational Bayes, where you might actually not characterize uncertainty very well at all. And so you might have an estimate of a posterior distribution that is much more concentrated than is realistic, given the actual uncertainty you have in a problem. And so we'd like to be able to actually accurately characterize uncertainty. Also, an issue that I'm going to touch on and in a chunk of this talk is on robustness of inferences. And so one thing that's really interesting is that, okay, we take a Bayesian approach. Well, a Bayesian approach is one example of a model-based approach to inference. And by model, I mean that we need to specify a likelihood function, a generative likelihood function for the data. It could be that likelihood function is very complicated and intricate to allow for a lot of flexibility. But then what we're worried about is this sort of robustness of inferences. And so that can be a particularly large problem as the sample size gets really big. And so it's kind of well known in statistics, for example. Let's say I have a likelihood or some base model, and I might want to be doing some type of hypothesis testing or variable selection or some other types of inferences on the model structure. Well, what often happens is, well, if the sample size gets bigger and bigger and bigger and bigger, then everything becomes significant. And so if we have millions of observations, all your p-values are significant, your model gets bigger and bigger and bigger, kind of without bound, and we become very non-robust in the sense. And so we might have a model that's really good, that could be very nice at interpreting the data, but then the actual data you observe might not be coming exactly from that model, because all models are wrong. It might be coming from a slight perturbation of that model, and that becomes a big issue when the sample size is really large. And so we end up having sort of less robust inferences as sample size becomes really, really big. And if we just care about some sort of predictive input-output black box, which is a lot of machine learning, then we might not care so much. But if we want to actually do kind of scientific inferences based on our model-based inferences, then it's a very big issue. And I'll discuss that. Okay, so that's the general focus. Obviously, we're going to be focusing on Bayesian approaches. I would say Bayesian methods offer an attractive general approach for modeling complicated data. And so to just sort of set the stage here, many of you, of course, will be familiar with basic Bayesian inference, but probably not all of you. And so here we're going to say, well, we have some sort of likelihood model. And so this is some generative probability model that could generate the data you observe. And I'm going to say that's Y. And I'm going to put a superscript n on that Y to index the sample size, okay? And so I might be dropping some of that fine notation as we go, but let's just say this is the likelihood of some giant collection of data Y, superscript n, and it's parameterized by some parameters theta, okay? So this might be some mixture model. It could be some sort of generative neural network. It could be a Gaussian process. It could be anything. And so that's our data. Here's our parameters. And so if we take a Bayesian approach, then we need to put down a prior probability distribution on these parameters, and I'll call that pi of theta, Okay, and so we have a prior, pi of theta. That sort of encodes information in the parameters prior to observing the current data. And now the likelihood is encoding information in the data about those parameters, and then we kind of put it into our Bayes rule. Okay, so here's the prior, here's the likelihood, and now we need to turn this into a probability distribution, and so we normalize it. So we divide by the integral of the prior times the likelihood over the parameter space. That's often known as the marginal likelihood or the evidence. Okay, and then we get this posterior probability distribution. So the Bayesian updating occurs when we update the information in the prior, which might be a relatively flat probability distribution, with the information in the likelihood, and then we're doing a type of learning. Okay, and that's one really nice thing in that we can keep doing that over and over again as we get more and different types and disparate sources of information. We can kind of keep plugging in and doing this Bayesian updating to learn ever more about this kind of posterior distribution as more data become available. Okay. The posterior is really nice in characterizing uncertainty in the parameters, and also, I would say, in any functional of interest. And because we might not be interested directly in these parameters theta. These are just parameters that are convenient to specify our likelihood function, you know. And so we might have a model like some sort of generative deep neural network with a lot of uninterpretable parameters, but we might be interested actually in some sort of function of the parameters that might be, for example, the mean output or some sort of percentile of an output given an input, something like that, okay? And so that might be our functional of interest. Parameters might not be interpretable, but the functional might be interpretable. Okay, and we might also be interested in predictive distributions, even marginalizing out the parameters as a sort of nuisance. We would like to get the predictive distribution for a new observation, given features on that new observation, using all the information we have so far. Okay, and we can do all that sort of thing using this kind of Bayesian calculus in some sense. Okay, so what's the problem? Well, you know, if you look at this equation, often the theta is moderate to high dimensional. And if you have an interesting model, not some really simple thing, then this integral down here is going to be some nasty beast. We're not very good at approximating high-dimensional integrals. There's been a lot of literature on that. Many different methods are proposed to kind of approximate this so-called marginal likelihood in the denominator, but many of these methods aren't very good. Okay, and so we run into problems computationally and kind of approximating this integral and hence approximating the posterior. Because often we have the prior and the likelihood. Sometimes we don't in so-called doubly intractable problems. But often we have the prior and the likelihood, but we can't evaluate this integral. Okay. Okay. So then the question is, well, in interesting models, the posterior is not available analytically. What the heck do we do? Okay. Well, one thing we could do, well, if we had a simple model, simple models are often called conjugate. Well, what's conjugate? So if the model's conjugate, then we can write everything down in a really simple form. So that means that the prior distribution, pi of theta, and the posterior distribution, pi of theta given y, are in the same form. And so maybe we start out with a Gaussian prior, and we update with a linear model, Gaussian linear model likelihood, and now the posterior is still Gaussian, okay? Or it's still a t, or normal inverse gamma distribution, or some sort of exponential family form, okay? And so if we have that type of conjugacy, then life is good. We can write down the posterior analytically, and we can do a lot of things, okay? And so that's often true even in somewhat interesting models. If you write down a linear model where you can have a lot of flexibility through some type of basis expansion, you can still get conjugacy. Okay, so in a more complicated settings, what we could do is we could potentially approximate the posterior using some tractable class of distributions, okay? And one popular class, which it's interesting to me, I think that, you know, machine learning, often people will focus on variational Bayes approximations, but there are actually these kind of classical approximations that might even often do better than variational Bayes approximations, particularly in terms of uncertainty quantification. And one is this just sort of good old large sample Gaussian approximation, okay? So what happens is if you have, under some regularity conditions that I'll sketch real quickly, if you have a big enough sample size, you know, and so that's what we're worried about. We have a huge sample size. How do we do computation? Well, often if the model's not that complicated, then the posterior is going to be approximately Gaussian anyway via what's called the Bayesian central limit theorem, often known as Bernstein-von Mises theorem or BVM theorems. Or, well, as the sample size gets big, we get approximately a Gaussian a limiting distribution, and we can easily calculate the mean and the covariance of the Gaussian, okay? And so this is relying on the sample size n being large relative to the number of parameters p. The likely it has to be smooth and differentiable, particularly around some sort of true value theta naught in the interior of the parameter space. And that really doesn't need to be the true value. It needs to be, essentially it's going to be concentrating around a theta naught, which is the best value of theta in the parametric class under consideration. And so if we had some likelihood function that we're parameterizing L of y given theta, it might be that the truth is outside of that class, but there's some minimal KL point outside of the class to the true data generating model, and then that theta naught within the class that's at the minimal KL point, that's where the posterior is going to concentrate, okay? And it's going to be eventually Gaussian under some of these types of conditions, okay? And I'd say, like I would say in most of the literature that I've looked at on scalable Bayesian inference, it's probably all of these conditions essentially hold, and we might have a large sample Gaussian where we did some sort of divide and conquer matrix tricks to calculate the mean and covariance might actually be competitive or better than many of the methods. Okay, another class of approximations which is really closely related to the large sample Gaussian approximation is the Laplace approximation. And so we could take this posterior back here, and then we'd say, oh, well, here's a hard integral that we can't calculate really easily, and so we could use Laplace's method to approximate that integral, and we end up with essentially a large sample Gaussian type approximation to the posterior, and that's called the Laplace approximation. And there's a really big literature on Laplace approximations. Often they do remarkably well. They do a good job at sort of characterizing the first and second moment of the posterior, whereas many variational methods might butcher the second moment. They're not going to do a good job at all if the posterior is like multimodal or skewed or weird. But, in large samples, if we have a, not too complicated model, then this kind of good old Laplace approximation, which has been around for a really long time, can do remarkably well. And I would encourage people working in scalable Bayes inference to compare to the Laplace approximation, which often they don't. And probably I could define a scalable Laplace approximation that beats your variational approximation. Okay. So that's a kind of really good, classic kind of old school Bayesian approximations in large sample sizes, okay? And we could certainly define scalable versions of them. So what could we do instead? Well, as an alternative to these kind of really old approximations, we could think of defining some type of approximating class Q of theta. So our posterior distribution is pi of theta given y, and that's intractable, and so we'd like to get close to it. So let's say, well, let's approximate it with some tractable class Q of theta. And then Q of theta might be something like a product of exponential family distributions parameterized by some, working parameter xi, which is just an algorithmic parameter controlling the accuracy of the approximation. And then we could think of to define some type of discrepancy between Q and pi, the target posterior distribution. And if we can then define some type of optimization problem to minimize this discrepancy, the resulting Q hat might give us a decent approximation. And variational Bayes is one flavor of this, but also expectation propagation and related methods. There's been a really interesting recent literature generalizing variational Bayes to use Bregman divergences, alpha divergences instead of Kolbeck-Leibler. And I'm not going to talk about that stuff very much today, but it's a quite interesting area. In terms of variational Bayes, I would encourage you to look at Tamara Broderick's really nice ICML 2018 tutorial where she gives a sort of state-of-the-art overview on variational methods. Okay, and so the variational methods are based on maximizing a lower bound, discarding an intractable term in the Kolbeck-Leibler divergence. The reason that I'm not going to talk about variational Bayes methods today is that, to me, the whole beauty and reason that I'm interested in this Bayesian formulation is I'd like to do a really good job characterizing uncertainty, okay? And if I have a variational Bayes approximation, I've thrown out an intractable term, and then I do all this, then I don't know what I have. I have some sort of approximation, but it's, to me, I'm I'm a mathematical statistician partly, and I'd like to know if I'm calling it an approximation, I have to have some sort of guarantees that it's actually approximating. Otherwise, it's like just something else. So I have something else, which is a Q of theta, which is in no sense really an approximation to a posterior distribution, and is really in no sense Bayesian. It might be useful from a machine learning perspective, but in most settings, I have actually no clue at all how well it's doing. I could see, but 99% of the time when people use it, they don't even look at how well it's doing in terms of uncertainty quantification. So I've become quite skeptical of these kind of variational Bayes type methods for those reasons, because we don't know that they're accurate at all. Okay, there is some really nice literature. Mike Jordan and Tamara Broderick and Giordano have this nice approach I really like, which kind of fixes up the uncertainty to kind of using a kind of linear approximation locally. So you can think of it almost like taking variational Bayes and then taking the Laplace approximation and losing a Laplace approximation to kind of fix up variational Bayes. It's not exactly that, but that's a kind of flavor of what you can do. So these types of fix-ups can improve the variance characterization in a local mode, but you don't know other than that. I'd also like to highlight a recent article. Maybe I'm biased towards this article since it's from 3 of my former students, Devdeep Padi, Anirban Bhattacharya, and Yun Yang, have this really nice article showing really strong theoretical guarantees on statistical optimality of variational Bayes, but they're doing it from a point estimation perspective, and so they can show that the variational posterior will actually concentrate in a very optimal way, giving you a wonderful point estimate, but not showing that the variance is right. Actually, they find that the variance is often very wrong. Okay, so there's no theory on accuracy of UQ. And so for this reason, I'm going to spend most of the talk really on Markov chain Monte Carlo methods. And it's been interesting to me that Markov chain Monte Carlo is this sort of now and kind of old school method for doing Bayesian computation. And I often find I hear a lot of talks where people will just discount it entirely. They'll say, well, MCMC is not scalable, so I'm going to use this variational approximation that I know nothing about, but at least I can compute it. But actually, there's now a really, really rich and beautiful literature emerging on how we can scale up Markov chain Monte Carlo. And I'd say it's just not the case anymore. You should not be making the statement that Markov chain Monte Carlo is not scalable. It's like saying anything else is not scalable. Oh, well, the M algorithm is not scalable. Well, that's because you're not using a scalable version. Okay, so if you just use a naive version of Markov chain Monte Carlo, yeah, it can be really bloody slow. But now we have a lot of tricks for scaling up Markov chain Monte Carlo, and there's an emerging beautiful theoretical and practical literature that I hope I can inspire some of you to add to in the coming years. Okay, and so the one reason that Markov chain Monte Carlo has kind of remained popular is that these analytic approximations like variational Bayes, we can't really show that they do well, and they might not do well outside of narrow settings. So Markov chain Monte Carlo and other posterior sampling algorithms provide an alternative, okay? And so, so MCMC, what the game is and the kind of beauty behind it in some sense is that we can take sampling, we have a sampling algorithm, and we set up a remarkably simple sampling algorithm where the stationary distribution of the samples is the true posterior distribution exactly, often, though we might put in approximations. And so the goal is to draw samples, not get an analytic approximation, but draw samples of pi of theta given y, the posterior distribution. And the one reason this is really nice is that, let's say we have a complicated analytic approximation of pi of theta given y. Well, that's really actually not that useful to me because, theta might be 1,000-dimensional. I can't visualize it, I can't do anything with it. And so really, I'm not ever usually interested in the full posterior distribution. I'm interested in some functionals. I want a one-dimensional functional, for example. I might want the predictive distribution of y for a new patient coming in, given their features or something like that. I'd like that, or I'd like to know something about particular functionals of the parameters that are interpretable, okay? But if I have an analytic approximation, I can't get that at all. But if I had samples from this, then I would have wonderful I could do a lot. I could just draw a bunch of samples. I could apply the functional to each sample, And then I can calculate any posterior summary I want. I can calculate the mean, I can calculate an interval, I can calculate a kernel smooth density estimate for that one-dimensional functional that I'm interested in. Okay? And that's usually how people do things in practice. And so samples, I don't see that there's a really good substitute for samples. Samples are not inherently slow or unscalable, and they give us an enormous amount of flexibility in terms of the types of inferences that we can do. Okay? Okay, so one of the beautiful things about Markov chain Monte Carlo is it bypasses the need to approximate the marginal likelihood. So that's this dude in the denominator down here. He's a horrible creature. And so there's all these papers on approximating the marginal likelihood, and basically all the algorithms are not very good. And I'd like to just avoid approximating this entirely, and MCMC cleverly does that. And so we only need to evaluate the numerator, and the denominator cancels. Okay. Yeah, and so this is just the point that the samples are often more useful than an analytic form anyway. Okay. Okay, so MCMC, what are we doing? So we're going to get MCMC-based summaries of the posterior for any functional f of theta. As the number of samples increases, these summaries become more accurate, okay? And so they're converging to the true posterior summaries. So how does MCMC work? So MCMC constructs a Markov chain with a stationary distribution that's a true posterior distribution. And to construct the Markov chain, we need what's called a transition kernel. And that transition kernel needs to follow some types of rules. And one of the classes of rules most of them are within what's called a Metropolis-Hastings algorithm. And the Metropolis-Hastings algorithm, to just give a bit of theory, certainly one of the most beautiful algorithms ever devised, in my view, certainly in the last 100 years. And the Metropolis-Hastings algorithm was originally published in a paper by Metropolis et al. in the 1950s, people working on the bomb. And then there was this beautiful paper by Hastings in 1970, which kind of took it and made it much broader, and that's the kind of giving us the kind of modern class of Metropolis-Hastings algorithms. And they're going to have a celebration of the Metropolis-Hastings algorithm, which was published in Biometrica in 1970, the 50th year anniversary. I'm going to be writing a kind of special paper highlighting that in Biometrica, which should appear next year. And so what the Metropolis-Hastings algorithm does is it's quite simple and broad. And so what we do is we would say, let's draw a candidate. So let's say theta star is drawn from some sort of g of theta t minus 1. And so the t minus 1 is denoting the t is indexing the MCMC iterate. And so we're running an iterative algorithm. Theta t minus 1 is the last iteration. Okay? And theta t is the sample at step t. So we draw a candidate for theta t, we call theta star, from some candidate generating density g, which might depend on the previous value of the parameter and on the data, okay? But it doesn't depend on farther away, and that's why it's a Markov chain. Okay, and then we accept the proposal by letting theta t equal theta star with this probability, which is just the minimum of 1, and throwing out this part, just a ratio of the prior times the likelihood at the candidate value divided by the prior times the likelihood at the previous value. Okay, and then the g just gives you an adjustment for asymmetry. And it's a Metropolis algorithm if there's no g, because we were limited to using a symmetric g and using Metropolis. Okay, so this is really simple. If we have some g, we can always sort of do this as long as we can evaluate the prior and the likelihood. Okay, so what's the game then? Well, if we wanted to do something efficient and particularly formally scalable to very large problem sizes, large n and p, then we need to choose a good proposal g. Okay, so g can depend on the previous value of theta and on the data, but not on farther back samples, except in what's called adaptive Metropolis-Hastings. And so the reason it's a Markov chain is that we're just sampling based on the previous value of the sample, but not 20 samples ago. So it's like a first-order Markov chain. So the special case is the Gibbs sampler. What the Gibbs sampler does is if we just say all the parameters are theta, it's a big giant vector parameters, we have theta 1 to theta p, then we can draw subsets of theta from their exact conditional posterior distributions fixing the others. We have a Gibbs sampler. And so what we might do there is it might be that, well, theta 1 is like, if we fix all the other parameters and go through the algebra, well, that might just be a Gaussian distribution. Theta 2, fixing all the parameters, might be a gamma distribution, and theta 3 might be a Poisson distribution, and we might just iterate through sampling from those conditional distributions. That would be a Gibbs sampler. Okay. That would be a special case in which the G cancels with the other part and we always accept. Another important special case is what's called a random walk. And so there we would start out, we're sitting there at theta t minus 1. We propose a proposal around theta t minus 1, just to say from a Gaussian distribution, and then we accept or reject. And that would be a random walk. Okay, and there's a quite interesting literature on how much are these types of random walks scalable to large dimensional problems. Okay. Some more fancy things that people have been using in recent years are like Hamiltonian Monte Carlo or Langevin algorithms. What they would do is they would try to design a really good G by exploiting gradient information, and so that we can get a draw from that's a really good draw but far from the current draw. So what we worry about is having a G which gives you a value really close, but then it's accepted with a high probability, but then it doesn't move far enough, and that can create inefficiency. So these HMC or Langevin algorithms are designed to overcome that. Okay, so let's get a little bit into the scalability. So what about why is MCMC thought to be slow? Well, potentially the time per iteration might increase with the number of parameters or unknowns, and can also increase with the sample size. Okay. This would also be true for just about every optimization algorithm in the world as well, but we can start there. Okay, so what happens is that we have to sample, and so what we're doing is we have to have the cost of sampling the proposal and also calculating the acceptance probability. And so if we think about just a simple random walk, we're drawing from a multivariate Gaussian distribution. Well, that might not be very expensive, but then we have to accept or reject. Well, that's a ratio of the prior times the likelihood. So we have to evaluate the likelihood. Okay. Well, that might be some sort of polynomial in the sample size evaluating the likelihood. Okay. And we have to do that to calculate the acceptance probability, and so that's going to be slow potentially. Or if we are sampling directly using Gibbs sampling, we might need to also sample from some sort of big Gaussian with a complicated covariance, which is hard to invert, and that might be some sort of polynomial in the sample size as well. Okay, so I would say that really the time per iteration cost is quite similar to costs that occur in many or most optimization algorithms, and we can do similar things in the MCMC context, even though we're not converging to a point estimate, but we're sampling and we're converging to a stationary distribution. Yeah, so an example is that the computational bottleneck might be attributable to gradient evaluations. And so we need to, in running Hamiltonian Monte Carlo, we need to evaluate the gradient a bunch of times. And well, what's the most popular algorithm in recent years for doing optimization? One of the most popular tricks is to cast a gradient, and so we could do that here as well. Okay, so that's the first type of computational bottleneck, is the time per iteration, okay, the time per iteration cost. And so that's very similar to the same thing in optimization algorithms. MCMC also has a potential second bottleneck, which might create problems. It's also similar to things that affect the convergence rate in optimization algorithms, because MCMC doesn't produce independent samples from the posterior distribution. So the draws are autocorrelated. What I mean by that is that the draw at theta t is going to be kind of correlated with theta t minus 1, and that's going to create sort of redundant information. And so if we could get independent draws, we might be getting much more information than we get out of the MCMC draws. Okay? And so that makes it so that we need to draw more samples than we would like because of this kind of autocorrelation or slow mixing problem. So the slow mixing Markov chain problem is what we're really worried about in these high dimensional cases, is increasing autocorrelation as the problem size increases. And this can occur both in N and in P. Okay. So a well-designed MCMC algorithm with a good proposal should ideally be kind of scalable in the sense of the mixing rate not getting worse and worse in the problem size. We don't want the mixing rate to kind of be exploding, and because what that means is basically the correlation is going up in the samples, and so we need to run more and more iterations the larger and larger the problem. Okay, and then we also have a greater per iteration computational cost, and that's where MCMC will grind to a halt. Okay, and we need to be clever in improving it. Yes, so otherwise the Monte Carlo error and posterior summaries might be high. And what we like to target in terms of scalability is, let's say we run the algorithm for some particular computational clock time or something, we run it for 5 minutes on a particular platform, then we would like the error in the Monte Carlo error and posterior summaries of interest to be as small as possible. Okay, we'd like to design the algorithm targeted towards small Monte Carlo error in a given computational time. Okay, so often the mixing gets worse as the problem size grows, data dimension or sample size. So in some cases we might have a double bottleneck, is worsening mixing, and we can think of mixing, it's similar to optimization problems with convergence rate. And so our problem is too much autocorrelation. It's sort of related to a problem of slow convergence rate. And we have a worsening time per iteration. Another issue that we run into is that MCMC is inherently a serial algorithm, so a naive implementation might require storing and processing all of the data on one machine. And so if we just take all the data on one machine, and it's just enormous amounts of crap in memory, and then we're trying to do like this kind of iterative algorithm and like one processor, then everything's going to be horrible, of course, and so we need to be smarter than that. But it limits the ease at which divide and conquer strategies can be applied. Okay, so these are the reasons that it's commonly just stated that MCMC is just simply not scalable. But I would say that each of the above problems can be addressed. There's already methods in the literature, and there's going to be a kind of rich emerging literature in this area, I think. And I would say that this is particularly promising because there's at least an order of magnitude, if not orders of magnitude, more people working on optimization and trying to develop scalable optimization algorithms than there are working on scalable sampling algorithms. There's really not only a handful of people working on these problems, and even given that, there's already been some really quite nice developments, and I think that that's quite promising. Okay, so for an MCMC algorithm to be scalable, the Monte Carlo error and the posterior summaries based on running for some time tau should not explode with dimensionality. Some popular algorithms have been shown to not be scalable, while others can be made scalable. And that's one interesting thing. Like we were working recently, one of the most popular algorithms for Bayesian computation and categorical data models is data augmentation, where you will throw in a bunch of latent data. You'll sample a bunch of latent data. You want to run a Gibbs sampler instead of having to tune some Metropolis Hastings algorithm. And so you'll sample a bunch of latent data. Okay, and then given the latent data, then you can sample all of the thetas from closed form, simple, full conditionals that might be normal or something. So we impute a bunch of latent data from truncated normals, and then we sample a bunch of parameters from a Gaussian. Okay, well actually you can show that often that's not very scalable, like in a theoretical way, and so maybe that's bad. And so just by using simple theory, well not so simple, theory arguments, you can see, well, this class of algorithms is very not scalable in this case, therefore we should just avoid them for theoretical reasons, and then we can focus on another class of algorithms. And I would say that this is an amazingly interesting area that I would encourage people to work on much more, is how can we develop more of that type of theory so we can use some sort of theory lens to target which algorithms that we can use in practice, which practical algorithms can be used in certain types of large problems. Okay. So anyway, so that's my very long introduction in some sense, but I'm going to focus on highlighting some of the relevant recent work, starting by focusing on big N problems and then transitioning to big P. And I'm going to give a disclaimer in that I'm just, given the time, I'm not providing like an overview of the literature, but I'm just focusing on some of the work we've done, and I'll give references, and then we've cited the broader literature in our papers. Okay, so now we're on the big N, and I'll give a little bit before we break. Okay, so some solutions to the big N problem. The first is what's called embarrassingly parallel Markov chain Monte Carlo. One of the types of solutions that I'm not going to talk about is to just take any MCMC algorithm and then say, well, maybe I can use GPUs or something to break up the computation. That I think is somewhat limited in scope because of the communication costs. And so if we really want to scale up, I'd say, well, we'd like to be able to have a giant data set stored on different computers, not be sending it around, not be sticking stuff on one computer, and limit communication costs. So maybe we can take the data and throw shards of the data on different computers, run MCMC in parallel for different subsets of the data, limit communication costs, and then combine, okay? And that's called EP-MCMC. And there's some really quite nice algorithms in that class by us and other groups as well. Another type of class of algorithms is what I might call approximate Markov chain Monte Carlo. Then we could just look at a Markov chain Monte Carlo algorithm and be like, well, geez, that gradient calculation is really bloody expensive. Let's use stochastic gradient there. Or over here, let's use some subset of the data. Or let's use some sort of low-rank approximation linear algebra trick here. And then we can free up the bottlenecks by taking a transition kernel that will converge to exactly the right target distribution and replacing it with some type of provably accurate approximation. And I would call that approximate MCMC. And these two can be used together as well, of course. Something that I haven't been talking about yet, but I will focus on a bit, is that we'd like to also develop robust methods. Kind of regardless of the scalability issue, we'd like to also have methods that are more inherently robust in large sample sizes, and we have such a method which I will highlight soon. Something I find really promising as well is to do type of hybrid algorithms. And so instead of running MCMC for everything, maybe we can use some sort of fast estimate for some of the parameters and then run MCMC for a subset of the parameters. We've had a lot of luck with this type of method, making it like very, very much scalable for very flexible models. You can scale as well as like state-of-the-art lasso algorithms for very complicated problems by doing a bit of optimization and then sampling for the rest. Okay, so I'm going to start out on this EP MCMC thread. And so the idea is that we have some big data set with really large N. We'd like to divide the data into subsets, and sometimes I find we're really kind of trying to work seriously on really large data problems. For example, we have a collaboration with Alibaba where they have really like billions and billions of users in different domains, and we'd like to be kind of applying these types of methods. And so we're kind of working seriously in these types of domains, also with SAS. And we find that often you can't really move the data around and have much control of the subsets, and so that's an interesting area, is to actually, where you're just kind of stuck with data on some machine from a particular client or some subset of users. We can't move things around that much, and so we have these data subsets. Here I'm going to focus on more intelligently constructed data subsets. Okay, so we take big data, we break it into shards, and then based on each shard of data, we get a subset posterior, and then we somehow combine them magically into a beautiful, accurate posterior approximation. Okay, so we're going to be drawing samples from each subset posterior in parallel, and then we get sort of atoms or a bunch of samples, and then based on the samples, we'd like to combine. So how can we do that? Well, here's this kind of toy example that's used a lot as a logistic regression, and so we might say, what's the label on the ith example given the vector features xi1 through xip and some parameters theta. Okay, and so that's just a logistic regression, and well, here shows a bunch of subset posteriors, and so we get a bunch of noisy approximations of the full data posterior. And you'd think usually often divide and conquer algorithms, we have a bunch of chunks of the data, and we get like some estimate of theta hat or something on each subset, and then we take the median or we combine them somehow. Well, here, the challenge is that we have a probability distribution. And so we have a full probability distribution for each subset. And, well, given only the subset, it should be like it's too variable, relative to the full data posterior is really this really concentrated thing around some value. Maybe it's even multimodal. And then the subset posteriors are like too variable, but they're all probability distributions. And so we end up with this really big problem. And how do we combine them? And so here I just shown some results where the contour plots for just two of the parameters based on MCMC, which we ran for a week or something, is here in blue. We have an approach called WASP, which is in red, which gives you a very accurate approximation, and in green shows the contours for the subset posteriors. Okay, so basically what we're going to do is use a type of stochastic approximation to the full data posterior distribution based on each subset, and we're going to average in some type of way geometrically to reduce noise. Okay, so it's a type of stochastic approximation algorithm that produces this. Okay, so we start out, we have the full data posterior distribution, pi of theta given y, and this is just some notation for that. We're going to divide the full data yn into k subsets of size m, okay? Break up all the data into shards, throw them on different machines or processors, and then based on each chunk of the data, y subscript j, in brackets, we define some sort of subset posterior. And the goal here is we'd like to take a subset of the data to give us a noisy approximation of the full data posterior distribution. Okay, and then we're going to sort of average those to get a really nice approximation of the full data posterior, reducing noise. And so how we do that is we take this is a likelihood for one observation. We take all those observations in that shard, and we're going to raise those likelihood to some power gamma. And so it's a type of gamma is this power chosen to minimize approximation error. Okay, but overall, the subset posterior just looks just like a posterior distribution, just with this tweak with this power gamma. Okay. Otherwise, we could just do MCMC within each subset, no problem. Okay, so then what we're going to do is we're going to use this notion of a Wasserstein-Berry center, which has become increasingly popular. I think a lot of people are interested in the machine learning and statistics and optimal transport problems, and so we're kind of defining things as a type of optimal transport problem. And so we're getting a bunch of noisy approximations to the full data posterior based on subsets, and we'd like to kind of take some sort of central approximation, our Berry center, and we're going to use that as our approximation. Okay, and so if we can define some sort of distance between probability measures, and we'll use the Wasserstein distance, then we can kind of solve this optimization problem to get a really nice approximation of the posterior. Okay, and so that's this kind of WASP method, or Wasserstein-Berry center of subset posteriors. We define a Wasserstein distance between probability distributions, and then we can just solve a type of optimization problem using this Wasserstein-Berry center, which is a well-known quantity in the optimization literature. Okay? And so one nice thing is that what we would do is we would take each of these subset posteriors, and we would get samples from them. And so in parallel, on each machine, we have a subset of the data. We run MCMC. That's easy because now the problem size isn't big because we have a small sample size on each machine. We just run it in parallel using whatever MCMC algorithm. We take those samples, we plug them into this discrete optimal transport problem to calculate the Berry center. It's a sparse linear program that we can calculate it very quickly, okay? And that's all we do. Okay. It also then gives you an atomic approximation, and because it's going to take those samples and reweight them, and then now at the end of the day, we're like, oh, we have weighted samples from the full posterior distribution given the whole data, and we can use that to calculate any posterior summaries we want for any functional just quite easily. Okay. Yeah, we're supposed to break, but I'll just finish up this shard of the talk. Okay, so the minimizing Wasserstein is a solution to a discrete optimal transport problem. We could say, oh, well, like a pair of subset posteriors we can write as like this atomic form. They're like weights on different atoms. The atoms we're taking by sampling from MCMC. We have a couple of probability distributions, and then we can define a matrix of square differences in the atoms. We can define what's called an optimal transportation polytope, and we can then solve this type of optimization problem using, just stuff that's already been developed in the literature for solving these types of optimal transport problems using sparse LP solvers. Okay? And one nice thing is that then we get this WASP posterior approximation, and we can prove lots of things about this approximation. It actually, is an accurate approximation, and it converges nicely about some optimal value of the parameters. And so I'm going to stop here because it's break time, because this is actually a simpler version that's, I think, much more useful in practice because we can actually bypass doing all of that optimal transport part, which makes things a lot easier. But I'll talk about that after the break. I think we have 10 minutes. Come back at 9:30. Okay, let's get started again. So this is another variant that's kind of similar, but that we just had published last year in Biometrica. So the idea here is that usually when we're doing Bayesian inference, we're almost always focusing on one-dimensional functionals. And so we have this joint posterior distribution, which might be for 5,000 parameters, but we're usually focusing on one-dimensional things when we're reporting the results. So the one-dimensional thing might be the probability of a class label or a predictive distribution or a parameter of interest or a functional of the parameters of interest. It's almost always a one-dimensional thing that we report at the end of the day. Okay. So we're reporting point and interval estimates for different 1D functionals. Okay, so keep that in mind. So if we do that and we think about, well, the Wasserstein-Berry center of the subsets it has an explicit relationship with the subset posteriors in 1D, okay? In particular, the quantiles are simple averages of quantiles of the subset posteriors, okay? And so this leads to a really trivial algorithm. And so the algorithm is super, super trivial. And so what we do is we have a giant data set, we break it up into shards, we throw those on different machines, we run MCMC in parallel with the likelihood raised to that power that I mentioned. And that's really easy. And okay, now what do we do? So now we're interested in some posterior functional, f of theta, or some predictive distribution, f of y given x, okay? Well, we keep track of that, samples from that on each machine. We calculate a percentile of the posterior distribution on each machine in parallel. We feed those back to the central processor and we average them, okay? And then we can, based on that, we can get a provably super accurate approximate 1D posterior approximation for any functional of interest and have very, very strong theoretical guarantees and good performance on those. And it's really, really easy. All we do is just break the data up, put it on different machines, run MCMC in parallel, calculate a percentile or quantile for any functional of interest, send those back to the central processor and average them. Okay. We didn't realize this at the time, but it's sort of reminiscent of a paper that Mike Jordan and collaborators came up with called Bag of Little Bootstraps. So it's sort of almost like an MCMC version of that. Okay, so we have quite nice theory showing accuracy of these approximations. You can potentially implement it in STAN, which is a sort of probabilistic programming language for Bayesian inference, because they allow powered likelihoods. Okay, I don't want to get too much into the theory today, but just say that as the subset sample size increases, it doesn't have to. It's not really dependent on the subset getting large, but as they grow really rapidly, we can have good accurate approximations. Okay, and so the bias variance is quantiles only differ in higher orders of the total sample size. Okay, so we've implemented this in a really broad variety of data and models. I don't have time to show results for this part today, but logistic linear random effects models, mixtures models, matrix factorizations for recommender systems, Gaussian process regression, non-parametric models, et cetera. So we can compare to long runs of MCMC and VB. It's much faster than MCMC doing this. And you get sort of a win-win because you think, well, the time per iteration is too slow as the sample size increases, and also the mixing might get worse with the sample size, but we're breaking up the data and running it in parallel, and so we're exploiting parallelization to improve the whole mixing issue and also massively improve the time per iteration, okay? I found that in many of these problems that there are actually quite good variational Bayes implementations that were competitive. Okay, so kind of given the time and what people were interested in over the break, I might just kind of skim through this part, but you remember that like in the big N case, there's these different types of methods. The one is EP MCMC. The second type of approach is approximate Markov chain Monte Carlo. And there's a rich literature on this. I just kind of listed this one archive paper by a really great former student of mine, James Jandro. But the idea here is that we have some MCMC algorithm that converges to exactly the right thing, but it's too slow. It's too expensive to evaluate the transition kernel. And so we might use instead an approximation. For example, we might approximate a conditional distribution in Gibbs sampling with a Gaussian or using a subsample of the data. And so that gives us a type of faster thing that we can sample from more quickly and approximate the actual conditional distribution. So using this trick, we can potentially vastly speed up MCMC sampling in high-dimensional settings. One example is that there's this huge literature on Gaussian processes where if I don't use an approximation, then I have an order n cubed matrix inversion bottleneck, and so then instead I use one of 100 different approximations that have been proposed in the literature that are low rank or nearest neighbor Gaussian process approximations or whatever. Okay, and so that would be a type of AMCMC. So the original MCMC sampler converges to the exact posterior distribution, but it's not necessarily clear what happens when we take that one and we perturb it. So we we have this transition kernel, now we've used this approximation. Well, does the thing even converge then? What does it converge to, et cetera? So, but this method is used routinely anyway, and often there's rich empirical evidence that the methods do quite well in terms of uncertainty quantification. Okay, so but we can develop some theory in this case. So we're going to define an exact MCMC algorithm which is computationally tractable but has good mixing, and we're going to leverage on that. Okay, and so we're going to approximate with a more computationally tractable alternative, and then we can kind of come up with a type of theory framework that we call comp minimax. And so you might have a particular computational budget, and then you want to have the optimal algorithm within some class of algorithms to produce the lowest error in a particular computational time. And so we can then get tight finite sample bounds on L2 error for a broad class of approximate Markov chain Monte Carlo algorithms. And you can see, well, which types of algorithms work. Well, often if, having a non-negligible approximation error works for low computational budgets, but as the computational budget increases, you want to have a more accurate approximation. Okay, so I'm just going to skip over this. You could do it for subsets, you can do it for binary outcomes, you can do it for mixture models, you can do it for GPs, et cetera. And so let's, I want to skip to the robustness problem. Okay, so this AMC, MC, EPMCMC, these are focused on providing algorithms for scaling up MCMC in a formal sense, in a practical sense, to large data problems. But then, we're trying to approximate the exact posterior distribution. And one thing we might worry about is that, well, the exact posterior distribution might not be very robust in large sample problems. And because in standard Bayesian inference, as in other model-based inferences, it's typically assumed that the model is correct. Okay? And so what we worry about is the one thing that having a model is nice in that the parameters might be interpretable. We'd like to kind of do inferences on these parameters. They might have physical meaning, et cetera. But small violations of the assumption that the model is correct can sometimes have a large impact, particularly in large data sets. It's a very famous quote is that all models are wrong, and the ability to carefully check modeling assumptions can kind of decrease for big and complicated data sets. So what we were interested in doing, and this is joint work with a former a postdoc, a brilliant guy who worked with me, Jeff Miller, who's now at Harvard in biostatistics, and we came up with this idea that you could maybe potentially tweak the Bayesian paradigm to be inherently more robust. And I'll give an example of the non-robustness here. So let's say we wanted to use a mixture of Gaussians for clustering. And so clustering is like, unsupervised, the big unsupervised learning problem. Model-based clustering is an incredibly popular type of method, and one type of very popular model-based clustering method is to mix Gaussians. Okay. Let's say that the true data distribution is like this. Okay. So we have a perturbed mixture of Gaussians, and so we're going to take a mixture of Gaussians, and then we're going to say the true model is not exactly a mixture of Gaussians. We're just going to change the distributions just slightly, so that a mixture of Gaussians would still be a nice approximation that we might want to use, and then we're going to see what happens as n increases. So going down here, we go from n equals 200 to n equals 20,000, and now we fit a model that allows the number of mixture components or clusters to be unknown. And what we see is that if we just even slightly perturb the Gaussians, you can see the red line versus the blue line, that we're going to keep adding mixture components without bound as the sample size goes up. So we're sort of making the model be more and more complicated, even though this mixture of two Gaussians provides a really accurate approximation. We would like to do that, but we instead add more components unnecessarily as the sample size increases. Yeah, so the point is that that's the right answer from a Bayesian perspective, is that we're allowing the model to be flexible. It can figure out which model to use using Bayesian model selection and averaging, but it's going to then introduce more and more components as the sample size increases to fit the data. And then the interpretability of the clusters breaks down in large sample sizes. And this is a very broad problem. It can occur, we've found, in many models, particularly when we have a model where the model's flexible. And so we're doing something like model averaging, or there's a set of models, and we have some sort of parameter controlling the complexity of the model. In general, as we add sample size, the complexity will be forced to increase because the model isn't exactly right. Here's a nice example to flow cytometry clustering. So each sample has 3 to 20 dimensional measurements on tens of thousands of cells. And here's like just a kind of 2 dimensions shown. And so here's like clusters. These are actually correspond to concretely to different cell types. And this is based on manual gating. And so somebody goes in and labels the data. And then here, if we use a mixture of Gaussians, it'll break up these like very non-Gaussian looking, but maybe approximately Gaussian into different subclusters and overcluster. Okay, so we'd like to do it automatically, but then these the kind of usual model-based clustering methods don't work very well, and distance-based clustering also doesn't work very well. Okay, so what can we do? So if the model's wrong, why don't we just fix it? Well, what we could do in this case is like, well, let's, instead of using a mixture of Gaussians, like come up with like a mixture of some strange kernel, and there's a literature on that, but it's kind of hard to do that, come up with these weird, kind of complicated, flexible kernels, and then we run into computational problems for, implementing these models with weird, flexible kernels. And so we maybe don't want to do that. Yes? Also, the simple model might be inappropriate, more appropriate even if it's slightly wrong. It might be that the data are always noisy. It might even be that the mixture Gaussians is right, but we just have some noise in the data, contamination in the data. Somebody's, typed in some observations that are slightly wrong, or there's some machine calibration issue. And so we'd like to allow for a slight degree of contamination. Okay. So what we proposed, this paper just came in JASA, is as follows. And so we call it C-Bayes, or a coarsened posterior. Maybe it's not a very sexy name, but C-Bayes. So here's the kind of setting. And so we're going to assume a model, P of theta and a prior pi of theta, okay? So we're going to say theta I represents the idealized distribution of the data. So that's over here. So theta I is the true state of nature about which one's interested in making inferences, okay? But then, we're going to say that the x1 to xn, or let's just say for now, are IID. You don't have to have IID in any of these methods, or unobserved idealized data, okay? But the observed data are actually slightly corrupted version. And so our observed data are never perfect. So we're saying like, well, there's these idealized data that we could have generated, but that would be under these very perfect conditions. In reality, we have these like error-prone conditions where we observe data little x1 to xn instead of idealized data big x1 to xn, okay? But, we think that, some deviance or statistical distribution are close for the observed data, little x1 to xn, and the corrupted data, okay? And so that's the game. So we're going to say if there were no corruption, we should use the standard posterior. That would be pi of theta given big X is equal to little x, okay? But due to corruption, that would be clearly incorrect, and that causes the problems with too many mixture components and the model growing in complexity with sample size. So instead, what we could do is we could condition on what is known, which is just pi of theta given some sort of the distribution of the data, the idealized data and the observed data, those two things are close. They're within R. So we can define some sort of discrepancy between the empirical distributions of the data observed and the data idealized data generated from the assumed model. Okay. So this seems kind of complicated, but it'll actually turn into something quite simple. So R might be difficult to choose, and so R is this sort of tuning parameter controlling the kind of model mismatch or model misspecification in some sense, and we could put a prior in the R, and then we could have some sort of class of posterior distributions. Okay. So what happens is that we could, to do this in practice, we need to choose a D, a discrepancy, as well as the R. So if we do something, in particular choosing relative entropy, and we go through some mathematical calculations, then we can show that the C posterior distribution, which is conditioning on this kind of event, is very close to this guy, okay? And so this guy is what? So this is the pi of theta, that's the prior distribution of theta, and now this is what we have in place of the likelihood, and like we have, there would be that wouldn't be there at all if we just had the regular likelihood and if the model was perfectly specified. But instead, due to the misspecification, we've raised to some power zeta n, okay, each of the observations, and the zeta n is just alpha over alpha plus n, okay? And so we've taken this likelihood, we've raised it to a power, and raising it to the power is going to automatically give us more robustness, okay, if we use this power, okay? And then we can, as in the EP-MCMC algorithms where we had a power, but the power was motivated by getting a good posterior approximation and parallel inference, Here we instead have a power that's motivated by robustness in large sample sizes. Okay? So the power posterior enables inference using standard techniques. We can use conjugate priors, or we can also use MCMC, just using this likelihood raised to a particular power. Okay, so I'll illustrate this kind of model misspecification issue with just this really simple coin flipping example. So let's say our interest was in testing whether or not the coin was unbiased or not. So we flip the coin a lot of times, and our null hypothesis is that theta is 0.5. So we have a 50% chance of a head. Okay, but then we say, well, the data in practice are a little corrupted, and so they might say they behave like Bernoulli 0.51 instead of 0.5. So if the null hypothesis was exactly true, it would be 0.5, but it's 0.51 in our data we observe. So our C posterior is robust to this, but the standard posterior is not. And so on the x-axis is the sample size. So the sample size is blowing up, and on the y-axis is the posterior probability of the null hypothesis given the data. Okay? And so technically the null hypothesis isn't true because it's 0.51, but it's really close to true. And so what we get is that, as the sample size increases, initially we're getting the exact posterior looks like it has evidence building up for the null hypothesis, and but then at some point it drops off, okay? Because then the data are big enough to show that, well, actually 0.51 isn't 0.5, okay? And we get this kind of problem. We also wanted to see whether we could do the same thing in mixture models or in many other models. And so let's say we have a model, x1 through xn, they're IID from some kernel mixture, and we do a Bayesian thing, and so we put a prior on the different parameters, and then we have this C posterior approximation, okay? And then we can run MCMC. So we could run MCMC for a mixture model, for model-based clustering, and compare our C posterior, or more robust posterior, to the exact one. And we have an MCMC algorithm that we could easily implement for quite large data sets, and then we could farther scale up using our previous tricks. Okay, so here's just some results. And so here I go back to that perturbed mixture of Gaussians where the true data generating model we've simulated is very close to a mixture of two Gaussians, but they're slightly perturbed. And then if we use a standard posterior, we keep adding Gaussian components as the sample size goes up. But if we use the C posterior, then that doesn't happen at all. Actually, we get consistent inferences as the sample size goes up. We're always choosing two components. Okay. And that also happens. It happens if we use 4 components and we perturb those as well. The same kind of deal. And we also got beautiful results in this quite important applied flow cytometry clustering data. Becomes much more robust, the clustering to the shape of the kernel, misspecification of the shape of the kernel. Okay, and we actually had a labeled data set, and from people going in manually and doing this manually gating to label the data. And we had a whole bunch of different labeled data sets, 7 through 12 here. And looking at an F measure, we did dramatically better than using a usual Bayesian posterior distribution in terms of clustering. Okay. So this C-Base provides a framework for improving robustness to model misspecification. It's particularly useful when interest is in model-based inferences instead of some black box. We want to interpret the parameters, for example, and the sample size is large. It can be implemented quite easily using MCMC and those scalable MCMC tricks we talked about earlier. Okay, I'm just going to skip that. Okay, so in the remaining time, I'd like to just transition to talking about high-dimensional data, okay, or big P. So we focused so far on solving computational robustness problems arising in large N. And I would say really many ways these problems are quite easier to deal with than issues with high-dimensional complicated data. So that is really, I would say, the most important problem moving forward, I think, in statistics and machine learning is how the hell do we deal with all these complicated data where we don't have a giant sample size? All this stuff with deep learning and everything has been very exciting, but usually in those settings we have really structured data and we have a big sample size, and we have a lot of labels, et cetera. Well, what if we have data that aren't so structured, or the structure's not so clear, and the sample size is enormous? I mean, the sample size isn't that big, but the dimension of the data is enormous. And so for each patient in a study, I've measured a billion different omics things about them, or I've taken brain scans in neuroscience and measured like their entire brain connectome, and we keep getting more and more and more higher resolution and better measuring technologies for massive dimensional data, but we really don't have statistical tools for making sense of it. And often what happens is it's this complete garbage in my mind in some sense, is that, okay, well, I have some data set, I have some outcome Y, and I have some features X, and the X is really high dimensional, and I don't have that big a sample size, and I'm doing basic science, or I'm doing medical research, or I'm doing neuroscience, and I go in and I fit some machine learning algorithm, I do random forest or a neural network, or I do lasso or something, or elastic net, and I get a lot of variables that are spit out. And the scientists are going to like interpret those variables, and then really that's really unreliable, and we're running into like a replicability crisis in science. And so we'd like to be able to say, in a lot of cases, I think that we'd like to be able to say that actually, scientists, we can't do what you'd like us to do. You've given us 1 billion predictors, and you've run this study on 10 mice or 20 patients. We can't actually decide which of those predictors are the important ones. That's just not going to work. We're on the wrong side of some horrible phase transition. But a lot of the algorithms in the literature is focusing on giving us positive results. Like I stick it in this optimization algorithm, here's my features. And it doesn't like flag and say, actually all your features are probably almost surely wrong. Like you've got all false positives and false negatives because the problem's too big. You have too high correlation, the dimension is too high. And so I want better ways to deal with uncertainty quantification. Give me negative results, give me realistic results, give me ways to like coarsen the questions being asked so that we can get something much more reliable and reproducible in these high dimensional settings. Is there a way to like learn better low dimensional structures more reliably, okay? And so that's really beyond Bayesian inference, but I would just like give a plea for many of you to kind of try to work on these types of problems with me. Not with me in particular, but you do it and then tell me how to do it. Okay, so that's the, so these are types of things I work on all the time. And so we have very few labeled data relative to data dimensionality. And it's really important as well that, even though you're like, oh, I'm in some medical context, I'd like to say diagnose a patient or tell me which treatment to give the patient. But we don't really want a black box for prediction. No doctor is going to use something that just says, oh, we should do this to this patient. They want to know why, how is it working, what features are important, et cetera. We often want to do some version of variable selection. Okay, so Bayes for big P, I'd say, is a huge topic. I'm just going to provide some vignettes to give a flavor in the remaining kind of 30 minutes before we run out of time. Okay, so one of the kind of very popular things in these types of scientific fields that I've just been talking about is to do some type of variable or feature selection. That's often the focus. Okay, so one example would be I have some phenotype or response variable for a patient Y, some health response. I work a lot on cancer genomics, so this might be your subtype of cancer. And then I have a lot of genetic variance, XJ, associated with that response, okay? But there might be, now I have all of these, like whole genome sequencing and all this stuff, and so there might be a lot of these guys. The sample size is going to be modest. The number of genetic variants is huge. So we have this large p, small n problem. So what do we do? So mostly what people do, beyond this kind of Bayes versus frequentist, but mostly what people do are two main approaches. The most popular, I would say, is what's called independent screening. And so we might look at some sort of statistical test for association between Y and XJ. We're going to do that separately for each J. To get a p-value and get 1 billion p-values and then threshold them or something. The other type of approach people use often is some sort of scalable penalized estimation or shrinkage, lasso, elastic net, et cetera, being popular examples. Okay, so we test for association between two variables at a time, a phenotype and a SNP. We repeat this for all possible pairs. We get an absurd number of p-values, and then we choose some sort of p-value threshold controlling the what's called the false discovery rate, using, for example, this Benjaminian-Hochberg threshold. Okay, and then we get a list of discoveries. So we've taken this huge number of biomarkers and we've reduced it to some number, and then now we can maybe run follow-up studies on that number to verify. Okay, so this is really commonly used. It's very appealing in its simplicity. It's quite scalable. We can do this in parallel. We're just doing a simple thing on little pieces of the data separately, and so it's quite nice in that sense. It's really widely used. There's a lot of false positives and negatives, obviously. For sparse data, it's a really big problem. We might have no power to detect anything. Just looking at a pair of variables at a time leads to limited insights. And so let's kind of go into the weeds here a little bit. And so let's say we have a linear regression model, okay? And so we have some response yi on patient I, and then we just say model the effect of all the biomarkers with some xi prime beta, a bunch of features, genetic features, and then their coefficients are beta. And let's just put a little Gaussian error on there. Okay, and so if we were, around a while ago before we started making p really big, we might just have done linear regression or least squares, okay? And we would just get beta hat as x prime x inverse, x prime y, okay? Everything's good because n is much bigger than p, and we can estimate these coefficients reliably using least squares. But what happens as p increases or the xi's become more correlated, the variance of that beta hat is going to blow up, and it's not going to be a very good estimator. Okay, and so if p is bigger than n, it's really not even going to exist. So we need to include some sort of outside or prior information in doing this, okay? And so in a Bayesian approach, what would we do? Well, we would choose a prior probability distribution pi of beta, characterizing our uncertainty in beta prior to observing the current data. And then we would use our Bayes rule that I described earlier to update the prior with information in the likelihood. So we'd have a posterior distribution of beta, given our response data y, our features x, and we would just plug it into Bayes rule as before. Okay, so if we have a normal linear regression model and we choose a Gaussian prior, then we have conjugacy, and we can just write down the posterior distribution of beta in this simple form. It's just a Gaussian distribution, and the posterior covariance is just going to be a part. This part contains information in the prior. This part contains information in the likelihood. It combines those two sources of information, kind of shrinking back the MLE towards zero. It's a type of shrinkage estimator. Okay, so that's shown in the posterior mean. Okay, so we can get the same answer by just solving this penalized optimization problem, which many people in this audience, I'm sure, have seen a million of these types of things. And so we just have, we're minimizing some least squares plus some penalty. And if we had a Gaussian prior, that would correspond to a L2 penalty. So this is known as ridge or L2 penalized regression. And so it has a dual interpretation as a Bayesian estimator under a Gaussian prior centered at 0, and a least squares estimator with a penalty on large coefficients and L2 penalty. Okay, so the game here is to introduce some bias, the maximum relative to the maximum likelihood estimator, while reducing the variance a lot to improve mean square error, and enable scaling to higher dimensional problems. Okay, so of course we can generalize that to a broad class of penalized loss functions where we have a least squares part for goodness of fit plus p of lambda of beta, and that's a penalty term, and we previously put L2, but we could put on an L1 penalty to have a lasso type procedure. And if we did that, there was a question at the break about the Bayesian lasso. Well, the Bayesian lasso would just be doing this, but we would put a prior on beta that would correspond to a double exponential distribution, and then the mode of the posterior is going to be exactly the solution to this optimization problem. Okay, the nice thing is that mode is then going to be sparse and contains exact zero values, hence the popularity of the lasso. Okay, so there's a huge literature proposing many different penalties, adaptive lasso, fused lasso, blah, blah, blah. In general, the methods only produce a sparse point estimate, and I would say are dangerous scientifically. And I work a lot in real problems with scientists. I'm funded by NIH and working on trying to kind of solve health problems using machine learning methods and statistical methods. And a lot of the times, these methods kind of pull you in. You do this kind of sparse point estimation, but then you kind of run into problems due to the lack of uncertainty quantification. Okay. Let's say there's a parallel Bayesian literature on shrinkage priors. Bayes lasso is actually not a very good shrinkage prior. I was talking about that over the break. It's kind of a really bad shrinkage prior. If we want to be able to deal with a sparse problem where we have, very high dimensional predictors, then the mode of the posterior is not something we particularly focus on. We care about the full posterior distribution. Then we want a prior that actually has concentration near 0 to shrink away the kind of noise parts or the small signals, and then has heavy tails to avoid overshrinking the large signals. And Bayes' lasso has only one parameter controlling the tails and the concentration around 0, so it's going to kind of overshrink the signals away from 0, and then kind of confound the kind of number of 0 signals with the number of non-zeros. And so it doesn't have enough flexibility. And so more the state of the art in Bayes shrinkage priors for high-dimensional problems, and we can apply them much more broadly than in regression. I would say horseshoe is the most popular, and then also generalized double Pareto and Dirichlet-Laplace. Okay, and these priors are designed to have this kind of more control over the shrinkage at 0 versus the tails. Okay, so what's an appropriate prior for a high-dimensional vector of coefficients? Many of the priors can be written in this, Nick Poulsen had a nice paper on this, and this global local scale mixture of Gaussian framework where the beta j's are drawn IID, conditionally IID, from this normal 0 psi j lambda, and then we put some sort of prior on psi j and on lambda. So these are the local scales, and this is a global scale. And then we would choose an appropriate f and g. This is the kind of game. And we would like to choose lambda to be kind of close to 0 to correspond to global sparsity, and then psi j to have heavy tails. Okay, so we have really a rich literature now on these methods. I'd like to kind of just highlight one paper which is by a really excellent student of mine, James Jandro, who's now a Stein Fellow at Stanford and on the job market. He has this paper where he kind of shows that you can take a horseshoe prior, and you can actually use some scalability tricks to show that theoretically you can scale up a prior to very high dimensional problems theoretically and practically. And so you can now deal with certainly hundreds of thousands of predictors using these types of Markov chain Monte Carlo algorithms. There's another really nice paper is by Martin Wainwright and Mike Jordan and a former student of mine, Yun Yang, in the Annals of Statistics, have a similar result showing scalability for spike slab priors. We have a formal mass at 0 mixed with another distribution, and then you're doing a stochastic search in a very high dimensional space. They show that also can be designed to be technically scalable in a CS sense. Okay. So features of a Bayesian approach. So a Bayesian approach provides a full posterior distribution characterizing uncertainty instead of just a sparse point estimate beta hat. And that I think is really, really, really important. And so by using MCMC, we can get credible bands. And so those are like Bayesian versions of confidence intervals. And so we can actually characterize uncertainty. So these are going to be confidence intervals for the beta j's, and for any functional of interest like the predictive distribution. And it's relatively straightforward to incorporate extensions to allow all sorts of like bells and whistles, hierarchical dependent structures, multivariate responses, missing data, et cetera, et cetera. But I would say that a couple of caveats and motivations for people who might want to do some research in this area are that I still don't really trust these methods very well. Sorry. I'm going to cough if I don't drink something. I really don't trust these methods very well, because what we do in practice is, in order to get good results, provably good results for really big P relative to N, then we kind of apply really an aggressive shrinkage prior. Okay, and so the prior is pretty shrinking really aggressively. Well, what if the truth is actually not that sparse, for example? Well, then our prior is actually really informative. We've had to make it really informative because the dimension of the data is much bigger than the sample size. If we don't make the prior really informative, then the posterior is just going to be really vague, and it's not going to concentrate around anything, and then we can't make sense of it. Maybe that would be the appropriate uncertainty quantification, but to try to get a good result, we've sort of put in a lot of information in the prior, maybe too much information in the prior, and then we look at these intervals, and they're really tight. And so I get a little bit skeptical about those intervals because they're so tight, and they're kind of putting in information in the prior as if the problem is really sparse. And so I think we all need to kind of think carefully about this kind of issue. It gives you uncertainty quantification, but it gives you it under a very informative prior. If you don't have a really informative prior, the posterior doesn't concentrate. Okay, so in the remainder, I'm going to give a couple of kind of vignettes about kind of different types of approaches, jumping into a couple of applications. that can be made scalable that I find kind of interesting. So here's one really cool application. So DNA methylation arrays. And so what's DNA methylation? And so we all have like our genome, you know, we have like our sequence, but actually there's all these CpG sites along our genome that can become methylated. And so like maybe by what we're exposed to, I'm drinking too much coffee or something, then I get certain regions methylated, and then that's going to impact gene expression. And so that can maybe impact, you know, my probability of getting diseases or other things about me. Okay, and so we'd like to understand the effect of this kind of epigenome corresponding to these DNA methylation sites, okay? And so now there's all sorts of like amazing biotechnology for measuring stuff like this, and so we can measure it across the whole genome, all of these different CpG sites. And so here we're analyzing data where we have 450,000 different CpG sites. There's even higher dimensional data available where we can look at across the entire genome for every individual in the study, okay? So what we'd like to do is we'd like to identify differentially methylated CpG sites, and there's a ton of them. But if we zoom in at any given location, like say these are the densities of DNA methylation for people with 2 different subtypes of cancer, for example, then we see that the densities are quite non-Gaussian, they're quite multimodal and strange looking. Okay, so how do we kind of develop some sort of scalable Bayesian statistical method? So here the measurements are in a 0-1 interval ranging from no methylation to fully methylated. And so the data from the Cancer Genome Atlas. Okay, so we observe data like this at a huge number of CpG sites. Many distributions share common attributes, modes, etc. And so we could you know, what would we do if we tried to build like a religious, fully Bayesian probability model? Then each individual would have a 450,000 dimensional response, and then we could try to like, what would you kind of build a mixture model for a 450,000 dimensional response? We really can't do that. And so what I'm going to do is I talked earlier about C-Bayes. Another thing that I really like that's been looked at in the recent literature is what's called modular Bayes. And so that's taking the Bayesian framework, but within a religious Bayesian framework, you would have to model everything jointly. You'd have to have a likelihood you believe for everything jointly. What modular Bayes does is it actually breaks up the data into modules, and you can like put a Bayesian model within each module, but the modules don't necessarily talk to each other. And there's a couple of reasons why that's really nice as a type of generalized Bayes procedure that does nice scalable uncertainty quantification. The first is that because the modules don't talk to each other, the model can be much more robust. And so sometimes fully Bayes joint models for high dimensional data can be brittle to model misspecification, okay, as I talked about earlier. But also, and if we have, they're much less brittle if we use a modular approach where we're modeling pieces of the data separately. Another really big reason, of course, is then scalability, because if we're modularizing and we have models for pieces of the data separately, then we can potentially do computation separately as well. So what I'm going to do here is I'm going to do a type of dictionary learning, basically. So I'd like to characterize hundreds or thousands or millions of these distributions using a small number of pieces and then reuse those pieces within a Bayesian model. So I'm going to use what's called a shared kernel mixture model, or SHARC. Okay, so we're going to use the same kernels across the sites and groups, but allow the weights to vary. Okay, so the methylation density at site J in group G, so there's different sites along the genome. Group is the different types of cancer group, okay? And so we could say, well, that density is FJG. So FJG of Y, that's the density of methylation at that site in that group. We can write that as a kernel mixture, okay? Of H components, and then we can put down some kernels, and now we're going to let the weights vary, but the kernels are common. So when you do that, we make the kernels common, we basically have like a ridiculously enormous, essentially infinite sample size for learning the kernels, because we get this kind of blessing of dimensionality across the different CpG sites. And so we don't need to characterize uncertainty in learning the kernels, because our data are so immense that if we characterize the uncertainty, the posterior would be just a point mass super concentrated on one value anyway. And so we're going to learn a fixed set of kernels and then put a posterior distribution characterizing uncertainty on the weights, with the weights vary across the different sites and groups. Okay, and so that's going to be the game. So these weights, pi jg, are weights specific to site J, group G. And so K is a shared kernel. So here we use the truncated normal. We can use any sort of like fancy kernel. Okay, so we're going to put a simple hierarchical model on the pi jg's, a Dirichlet in each group, and then we do a testing problem. Now we can do a scalable testing. I think testing is some problem that we often really have to do in scientific inferences, but machine learning people haven't focused on as much as I'd like. So here we have two different possibilities at each site. So the two different cancer subtype groups, they either have the same distribution of methylation or they have a different distribution of methylation. We'd like to identify the sites that are differentially methylated. Okay? And that's a multiple hypothesis testing problem. So we're going to put Dirichlet priors on each of these probability vectors within this hypothesis testing problem, and it's going to be automatically adjusting for a multiple testing error, controlling false discovery rate automatically within a Bayesian multiple testing framework. And the computation is extremely fast, because if we use fixed kernels, we get conjugacy everywhere else except for one little piece where we can just use a simple parallelized Gibbs sampler. And so we can run this for hundreds and hundreds and hundreds of thousands or millions of different sites quite seamlessly. And we have some theory I won't talk about. Okay, so we illustrated this using 597 breast cancer samples. Let's just show it for 21,000 CBG sites from this Cancer Genome Atlas. And here just shows the probability of the null hypothesis at each of the sites. So there's 21,022, almost 1,000 sites. And so this is just a histogram of the estimated posterior probabilities that there's no differential methylation. And so you see most of the sites are like, there's no difference between the cancer subtypes, but here there's a subset of sites having a high posterior probability of H0, meaning a low posterior probability of H0, meaning a high posterior probability that there's a difference. Okay, and so we can test differences between basal, like, and not at each site, and the global proportion of no difference was 0.821. So this is pretty cool, and then we could look at relationships with held out gene expression data and to kind of validate or have essentially labels on the results. And when we do that, we can see that this does massively better than other types of methods that people might use, just doing independent testing and then false discovery rate control. So this kind of Bayesian, it's really kind of Bayesian non-parametric multiple testing method kind of really has practical improvements. And the usual multiple testing method for frequentists would like separately at each site get a p-value, but they wouldn't be borrowing information across the sites. And so here, by using a Bayesian hierarchical model, you're borrowing information. Okay, so I'm going to give one last example before we run out of time, where we can do this same thing for really complicated outcome data. Okay, so what we're doing is we're characterizing non-parametrically the distribution within each group at each site using this kernel mixture model, and then we're letting the weights vary. So we're putting all the action in the weights to allow for testing, differences among groups, covariates, et cetera. So we can do this in a really complicated settings. So let's say we have brain connectomes, for example. And so here just shows like this is kind of a picture of in any given individual, I've taken a brain scan of everyone in the room, and then I've applied all this processing, and now I get the location of all these like white matter fiber tract bundles in your brain, and I have 1 million of those, and they're all spatially located, and that's my like complicated data I'd like to analyze. And I would say that that's what where the action's going to be moving forward is like, well, how the hell do we like analyze this kind of amazingly rich data collected from this new biotechnology without just using kind of simple off-the-shelf methods, but having methods that are appropriate for really actually complicated data. Okay, so let's say we represent the data as xi, which is a network or a graph, really, for each individual. So xi uv is 1 if there's any connection between regions u and v for individual I, and xi uv equals 0 otherwise. Okay, so we need some sort of model for non-parametrically characterizing variation in these brain networks across individuals. Okay, so xi is drawn from some p. What the hell is p? P is some distribution of random graphs. Okay, and they sure as hell don't follow some sort of stochastic block model or whatever the usual random graphs people use. So we can define some type of model, let's say for each brain region R and component H, we can assign some sort of individual specific score, and then we can put down a model, a simple hierarchical model, latent space model for brain networks. And so here is the logit of the probability that we have a connection between regions U and V in the brain of individual I. We can write as an intercept part that's common across the different individuals, characterizing commonalities in brain structure across different people. And then we have this kind of almost singular value decomposition or principal components type piece. The data are symmetric, and so we have like a sum from H equals 1 to K, different latent components, lambda IH, some weight specific to individual I, component H, and then we have some sort of eta part characterizing specific to the different brain regions. Okay, and then we can stack all the individual specific parameters into some theta I vector, and those are sort of random effects characterizing variation across individuals. And so this is sort of an example of Bayesian hierarchical modeling for high-dimensional complicated data. So we'd write down some model where we're characterizing variation in complicated data through some latent variables. And so this is quite a common kind of canonical game in Bayesian modeling of high-dimensional data. And then we don't know what the distribution of those random effects is. And so here we're going to use Bayesian nonparametrics to allow Q, the distribution of the random effects, and hence P, the distribution of the brain networks across people, to be unknown. Okay, so based on this framework, you're actually clustering individuals in terms of their brain structure, which is pretty cool. And we can test for relationships between brain structure and traits and genotype. Okay, so we just allow the weights in our mixture model to vary with traits with these fixed kernels. So the kernels are characterizing the kind of, provide a dictionary with which we can characterize brain graphs. Okay, and so this allows scientific inferences on global and local differences in network structure with traits. And I really think we need more of these types of kind of scalable methods with uncertainty quantification for complex data. And so I'd really encourage more people to work on this type of thing, not necessarily for brain networks, but for any kind of complicated data. Just for multiple testing as well. Okay, so here are some results. And so we applied the model to brain networks of 36 subjects, 19 with high creativity, 17 with low creativity, measured with the composite creativity index. It gives us an overall probability, a posterior probability, that there's any differences in brain structure with creativity, and that was 0.995, which is quite strong evidence. And we also, like you can see here, what we did here is we can flag statistically significant, after adjusting for multiple testing, differences in brain structure. And so a red line would mean that people with low creativity have more connections in that location. And so a green line means less connections. So what this green line here means is that the individuals with low creativity have significantly less connections between these regions, okay? And so we can see a lot of green lines that are cross-hemisphere connections in the frontal lobe of the brain. And so what that means essentially is that people who are highly creative have more cross-hemisphere connections, more connections that occur in sort of unanticipated regions, okay? And it was an interesting side comment is we had a press release on this result, and this left brain, right brain hypothesis, this whole thing where like left brain people are like more mathematical and right brain people are more creative or whatever. The guy who came up with this, he's deceased now, but his son contacted us and said, well, actually his dad like ended up not believing the right brain, left brain thing at all. And what he ended up believing was much more consistent with our thing, which was there's not left brain, right brain, it's more interconnected brains that are more creative. The left brain, right brain thing is just bogus. Okay, so the idea, just wrapping up, is that in this kind of modularization strategy, which I illustrated through that DNA methylation example, is we don't allow for all the dependencies implied by the joint Bayesian model. I think I kind of said that already. I think we have like 5 minutes. I'd like to take some questions, and so I'm just going to skip this. So the bottom line here is that we can scale up Bayesian inferences for genomic problems with tens of millions of SNPs using these same types of methods that I've been talking about. And so it's not true at all that Bayesian inference isn't scalable. We can deal with hundreds of millions of SNPs even, or features in regression problems, and we can use these types of methods. Okay, so discussion. So I kind of gave a brief intro to Bayesian methods for large P problems at the end of this talk. I highlighted some recent work using shared kernels and modularization. I'd say there's really a rich literature that's just kind of beginning and an increasing focus on scalability, and I hope to inspire some people to work more in these areas. And one important direction is to obtain methods for assessing when we're attempting inferences on too fine a scale for our data. I think that's really important to come up with more negative results. I mean, like, in these problems, I work with scientists all the time. I want to be able to tell them, like, actually the questions you're trying to ask are not possible given the data you've provided me and the prior information that we have. And so if I'm going to answer your questions, then I have to put more prior information in the analysis than I actually have, which is probably a bad idea. And so therefore, maybe I can come up with a method that will say, no, you can't answer those questions. Maybe it can then even go beyond that, almost like in an artificial intelligence way, and say, well, here are these questions you can answer. You can have like an assistant, like a Bayesian assistant that can say, well, the questions you're trying to ask are impossible. Why don't you ask these types of questions? These are the types of questions you can ask. You can't identify individual SNPs that are related to the phenotype. You can only identify regions of the genome, for example. So that would be incredibly useful. And there's really nothing like that out there now. So one way is to coarsen the scale of the data. Here's some references on large N. I'm happy to provide the slides to anyone. I can post them on my website, and then please email me if you have any comments, etc. The take-home message is just that Bayes is scalable and MCMC is scalable, but in big and high-dimensional problems, you can't just use off-the-shelf algorithms. You have to be smart about it. And we need to think carefully about how to exploit parallel processing, accurate approximations to reduce bottlenecks. We might also need to take a step away from fully Bayes frameworks by using modularization, composite likelihood, C-Bayes, etc. And we'd like to be able to design algorithms and inference frameworks that are improved in a computational way and in terms of robustness. And I'll stop there.
Thanks a lot, David. Very, very inspiring talk. So we have time for a few questions, if there are any. There are microphones here in the front, so please use them. In case there are no questions, I might ask one.
Hello?
Oh, there's one. Sorry. Yep. Beautiful.
Hi, thank you very much. It was very illuminating talk. My question is about calibration. So any Bayesian framework starts with likelihood function, which is a conditional of your observed data on whatever latent parameters theta you choose. Then you start with the priors, and then through Monte Carlo or whatever, you essentially can describe posteriors, and you can also describe the marginals. So, and quite often it happens that, yeah, and of course this likelihood function is a parametric model, and you know, the real problems are very complex. It's very hard to actually analytically write that likelihood function. So in the end of the day, when everything is done and one computes the marginal of the data and computes the quantiles, for example, you had an example of single dimensional distribution at the end, marginalize everything, and for single quantile function, then you get the quantiles which are different from what you observe in the data. So essentially the model is miscalibrated. And the model had like hundreds of the parameters, so what exactly should be the approach to recalibrate model back?
Yeah, that's a really great question. I'll first note that it's really important to look at calibration. And so often using out of sample assessments, and then calibration in the sense of not just point estimates, but that the probability distribution is characterizing uncertainty well in terms of predictive distributions. When the model is not well calibrated, I often think to try to put in more flexibility somehow. I don't know that there's a great answer for, okay, well, where did I go wrong exactly? It's in a complicated setting. It's not well calibrated. But the kind of rule of thumb in some sense is to, well, maybe I need some more flexibility, and so then I can go back and try to do some diagnostics to try to figure out where my model is not fitting very well and kind of iterate from there.
Thank you.
Okay. Hi. Two short questions. One question concerning the example that you make on the Bernoulli case, coin flipping. In that case, the test is at a certain point telling you that your hypothesis is false. So isn't that just the right answer? I mean, at some point you have enough power to refute the hypothesis. The hypothesis is false, and so
yeah, that's a great question. I think that's one of the philosophical issues. A lot of people don't believe in testing because they never believe in precisely that exact specification of the hypothesis, and it's related to this modelness specification. It was also doing the right thing in terms of the mixture model in adding more components, because it wasn't precisely two components that were true. But I would say that, practically allowing a tiny bit, a small amount of misspecification of the hypothesis in the model is going to give you much better performance, because in reality, you're never going to have exactly the data you observed or from exactly a particular hypothesis or exactly a particular model. And so you'd like to allow some sort of fudge factor there to allow them to be close but not exactly equal.
Okay. The other question, we are applying the, sorry, by the way, Andrea Panezza, Baker and Hughes, G company. We are applying the Kennedy and O'Hagan framework to so it's Bayesian calibration for computer models, okay, to a problem where basically we know that Gaussian process regression is not appropriate, or at least a standard Gaussian process, because we are sure that it's not, the model is, the variance is not isotropic.
Yeah, that's a great problem. I mean, this computer model emulation literature is really cool, but often the Gaussian process falls flat, and so better models for emulation is a good, important area.
So, yeah, in that case, what could be an alternative to using variational base? Because it's like we have, let's say, 500,000 samples, and it's a 14-dimensional problem. So it's, I mean, not big P, but relatively large N. So instead, then trying variational base that usually works well.
Yeah, certainly you could use these EP-MCMC kind of methods in that setting. They've been used for Gaussian processes, but even if the Gaussian process didn't hold exactly, you could even use them for something like, I know, one of our projects is using deep neural networks for emulation instead, and you can even run MCMC for deep neural networks, and you could do that in a parallel way, something like that.
Okay, thank you.
I was also going to ask about the C-base. I found that quite intriguing, and I guess it seems like what you've actually done there is replace having an explicit noise model with something non-parametric. So is actually what this is doing is corresponding to having some non-parametric noise model, but then, it's just...
That's a great question, yeah. We often get a lot of questions on C-base, whether it's like exactly the same as an explicit noise model, but it's sort of like avoiding specifying the noise model, because the noise model might also be misspecified, et cetera. And so it is like being non-parametric, but not non-parametric in the Bayesian non-parametric way, which means a really flexible model, but more non-parametric in the classical way where you avoid modeling something.
So my question is mostly referred in terms of scalability. Usually you said that probably most of the problems are kind of scalable in terms of like robustness. In which cases you have faced this challenge to scale, to make it scale, or to where the actual training, the full training is much, much accurate that trying to do mini bootstraps, for example?
Yeah, that's a great question. I mean, so this is really a new literature, and so there are definitely areas that are not developed well at all. And I would say that two of those are, network structured data and time series data. And so if you have like a really like super long time series, and you're trying to scale it up, like scale up these MCMC methods, there's almost no literature on that. There's a tiny bit by Emily Fox's group on hidden Markov models, and we just posted a paper on an archive for hidden Markov models, but there's no like useful general methods. And that's even more true in the network case. We have billions of users and products in this Alibaba collaboration, and we're kind of trying to develop scalable Bayesian methods in that case is a challenge, because if you're just kind of subsampling or breaking up the data, well, how do you do that if the data are really dependent in like a network context? It's an open problem.
So do you have a kind of initial guesses about that, especially for the time series data?
Sure, yeah, time series data, the initial guess would be to bin time, and so if you have chunks of adjacent time points, and then you can do computation in parallel for adjacent time points, then you can kind of do a lot in terms of scalability doing that. I think that'll end up working quite well.
Okay, thank you.
Hi, thanks for your talk. It's very interesting. I guess what wasn't really clear to me is if we have a lot of data, are you really getting a different conclusion using Bayesian methods versus using some more classical methods?
Yeah, that's a great question. I mean, I think that you hopefully shouldn't. If you're like in a setting where you have a ton of data and the sort of number of parameters isn't that giant. So if I have a logistic regression and I have maybe 100 predictors, but my sample size is 100 million or something, hopefully I'm getting exactly the same results. And we can show that theoretically, actually, with that Bayesian central limit theorem or Bernstein-von Mises result. The Bayesian posterior is actually going to converge to exactly around the maximum likelihood estimates, with the covariance being the inverse Fisher information. And so there's this well-known equivalence between Bayes and frequentist methods. Where the equivalence doesn't hold is when you're in these more challenging problems, certainly, where you have you have uncertainty remaining. It's not well characterized by a large sample Gaussian distribution.
Thanks.
You mentioned that there's orders of magnitude more people working on optimization, distributed optimization techniques. Is there any way or literature of applying these distributed optimization techniques to scalable Bayesian MCMC methods?
That's a great question. I mean, that's actually what we were trying to do in that WASP method or something. Like, so we do separate sampling, but then use modern optimization techniques for doing the combining. But there's also, a really amazingly cool literature that I didn't have time to talk about, like by people like Youssef Marzouk at MIT, trying to do things like, let's try to sample IID from a multivariate Gaussian, but define some optimal transportation plan to the true posterior distribution, and then define some corresponding optimization problem, solve that optimization problem. Well, if I have the map, then I just take those independent samples and I transform them to get perfect samples from the posterior. So there's a number of people working on that. Guang Cheng at Purdue is another one. Yeah, that's a great question.
Thanks.
You briefly mentioned that.
Sorry, I think we need to break for the coffee break. But feel free to come forward, and we can chat offline afterwards. But let's thank David again. Thanks a lot.